Hello everyone. In this video, we will be discussing two major topics. First one is how finite element method help the design engineering, and second one is steps involved in the finite element method. So first we shall discuss about how can the finite element method help the design engineers. The finite element methods offer many important advantages to the design engineer. So what are all they? First one, easily applied to complex irregular shaped bodies composed of several different materials and having complex boundary conditions. So if you take any example of practical structures, particularly engineering structures, where all these things we can able to see, that is the complexity we can able to see. Complexity means maybe the loading conditions or the boundary conditions or size, and second one is nothing but irregular shaped bodies or objects. So if you take any one particular applications where it may be a assemblage of 50 to 100 parts, so all the parts will be having the irregular shapes, so that also is composed together, and even different materials, all the 50 100 parts also not made with the single material, even it is composed of different materials, so that also. And second thing, and that can these engineers can able to identify, and even they can able to segregate it part by part, material wise, even the boundary conditions. Second thing is it is applicable to steady state, time dependent and eigenvalue problems. So all these things it is applicable. Next thing is applicable to linear and non-linear problems. Even in the previous videos I explained one example, the structural examples, where I've shown you an aircraft wing, so where both linear and non-linear properties and even the outputs also we discussed there. One method we can solve a wide variety of problems, including problems in solid missions, fluid mechanics, chemical reactions, electromagnetics, biomechanics, heat transfer and acoustics, to name a few. Here very few applications I have just discussed. So correctly speaking, more than this, almost we can say like without finite element analysis, any engineering domain cannot finish their analysis. We can even strongly say to that extent. Simulations using the finite element method also offers important business advantages to the design organizations. Number one, it reducing the testing and the redesign cost, thereby shortening the product development time. Because when we are doing it manually, there may be a like a time loss, even whatever the capital investments we have made for the testing and designing, it is of course waste. But when we are doing it by using any softwares, where those things can be avoided. Next is identify issues in designs before tooling is committed, and refining components before dependencies to other components prohibit changes. Even this is also possible. For example, when you are doing any particular continuum analysis, where you come to know that there is a problem in the aspect ratio for some of the elements. Such situation, the refining options is there, but when you are doing it manually, it is very difficult to identify and even to do the change. It takes a lot of time. But when you are doing by using a software as a design engineer, you could crack it within 2 or 3 minutes. If it is a complicated structure, so of course a similar simple structure mean hardly it will take some 5 to 10 seconds to refine the components. Next one is optimize performance before prototyping. This is also very an important thing. When we are doing it manually, once the prototype is made only, we can see that to which extent the durability and the working conditions and all is there. But in case of the designing purpose, I mean in case of the designing, where optimization is possible, where so that we can able to refine it till we feel that okay, this is the required one we are looking for. And next one is discovering the design problems before litigation. So even sometimes most of the design engineers may not be knowing what is the output, but when they start do, or when they start focus on this particular work, they may start discover many things which will be really pave the base to the new findings. So the next part, that is the basic steps and the phases involved in finite element analysis. This is applicable for the structures, the structural analysis. Maybe for the heat transfer and other things also there may be a slight changes, but these steps is properly applicable for the structural analysis. So the very first step is nothing but the discretization. So discretization is nothing but, say for example, a structure is given, a cantilever beam. Just for example, consider a cantilever beam or any other complicated structure, easy structure, you take it, and a tapered bar, anything you take it, not an issue. Discretization is nothing but whatever the given geometry in the problem, that we will be recreating the shape and size and like geometry as it is, and that later we will be dividing that into finite number of elements after identifying where the critical areas, focusing more number of elements on those regions, and smaller size elements, and we will be establishing bigger size elements in the areas where the critical area or critical points are not there. After the discretization, we will be going for selection of an approximation functions. Say for example, I have considered a tapered bar. In the tapered bar, I have divided totally into some 5 elements. According to the criticality, the third and fourth elements I have gone with the smaller size element. Remaining elements have gone with the bigger size element. I need to create the approximate function. It may be a polynomial function or it may be a trigonometric function. I will be selecting the approximate function for all the 4-5 elements. And next one is nothing but formation of the elemental stiffness matrix. If I am talking about the structural analysis, means first we should be knowing what type of elements I will be using. 1D elements, 2D elements, 3D elements, or axisymmetric elements. Accordingly, I will be deriving the stiffness matrix for that particular element, and I will be writing the element stiffness matrix. Next step is nothing but formation of the total stiffness matrix. So what does this means? So in the previous in this particular step, I have taken a tapered bar of 5 elements. So stiffness matrix for 1D elements, it is K. If I know the equation, I will be finding out the element stiffness matrix for all 5 elements, that is K1, K2, K3, K4, K5. That is nothing but formation of the element stiffness matrix individually, and formation of total stiffness matrix nothing but assembling all the 5 element stiffness matrix together considering the degrees of freedom. And next one is nothing but formation of element loading matrix. So this is nothing but the boundary condition. A cantilever beam, a point load is upright, means what is the boundary condition? Left side it is fixed in all DOF, right side a load according to which direction load is acting. That is nothing but the boundary condition. Again, that I will be writing by using the matrix vectors and the proper formulas. Next one is nothing but the formation of the total loading matrix. Again, individually I will be writing out for element wise, element 1, element 2, element 3, element 4 and element 5, and later I will be assembling all the elements. So that is nothing but formation of total loading matrix. So next step will be formation of the overall equilibrium equation. So the equilibrium equation is very it is almost common for all the structural analysis, that is K into U, which is equal to F. So K is the global stiffness matrix, U is nothing but the displacement matrix, and F is nothing but the load matrix or the force matrix. And next one is nothing but the implementation of the boundary conditions. In case of the structural analysis, we have 2 methods we will be following usually. First one is nothing but the penalty approach method, second one is nothing but the elimination approach method. By using any one method out of these two, and we'll be applying this boundary condition and we'll be finding out the unknowns, because already we would have taken one approximate function, either polynomial function or trigonometric functions. So by using applying this boundary condition, we'll be finding out the unknowns. So what are all the unknowns we'll be finding out? The major unknowns for all the structural analysis will be calculation of unknown nodal displacements will be finding out. Again, in your discretization, if you would have made 6 elements, 7 elements, 8 elements, means each element is having its respective nodes, and all the respective nodes it is possible to find out the nodal displacement and stresses. The last step is nothing but calculation of stresses, strains and reactions. So stresses and strains can be calculated only for the elements, but no displacement can be calculated for the nodes, that is the point where the element has been connected. So this is the steps usually we will be using to find out the solutions. So again I will repeat the names of the steps. Step 1 is discretization. Step 2 is the selection of approximation of function. Step 3 is the formation of elemental stiffness matrix. Step 4 is formation of the total stiffness matrix. Step 5 is the formation of the element loading matrix. Step 6 is the formation of the total